Hello, and welcome back to AP Environmental Science. Today, I want to talk about water. So your first question is, the amount accessible fresh water on Earth is about how much? Well, it turns out that 2.5% of all the water on Earth is fresh, but my question is about accessible fresh water, and the answer is 0.8%. When we start looking at how much water we actually have that's available for use, it's less than 1% because a good portion of that 2.5% fresh water is actually ice caps and glaciers. Almost 70% of all of the water is going to be locked up in ice. And then another almost 30% is going to be groundwater. And so surface water is actually less than 1%. So when it turns out that we are talking about, oh, how much water do we have and blah, 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 well, the vast majority of it is unusable, whether it's that 97.5% salt water or that, 1.7% ice or, the groundwater. Now, here's the thing about groundwater. It is on the accessible freshwater list for us. It's something we are going to talk about, but it can be challenging to get to, and we'll talk about that later on. All right, so here's the thing. I want to talk a little bit about the water cycle. The water cycle is something that you have seen before, but I want to highlight some of the terms that you need to know. Obviously, we're going to start in the ocean, right? So in the ocean, this is where you have evaporation. Okay, you have evaporation from all surface water, by the way. See, you've got freshwater evaporation, but the vast majority of the water that shows up in the atmosphere is going to be evaporating from the ocean. As it rises, look, see, there it is. This word is bigger than that word. As it rises, it condenses as the atmosphere cools off. And this is where you get clouds, so condensation. Yeah, it's going to travel with the wind cycles and the big atmospheric currents, and we get this wonderful sort of weather story that we have. Also, the long-term weather is climate, and we will talk about that as well. Not today, but we will talk about that. So in the atmosphere, it's going to travel around. Eventually, there's going to be enough condensation that we will get precipitation. Precipitation can come in lots of forms. It can come in rain, sleet, snow, hail, whatever. It's just water falling from the sky. And when it rains, it lands on the surface, right? And that water will either run off, which means it stays on the surface and flows along the top of the surface. It will end up in a stream or river, which possibly could land yourself in a lake, and it will eventually flow to the ocean. Okay. Now, some of that water will infiltrate, and infiltrate means to seep into the ground. It will then percolate, and percolate is not a word on this chart right here. But percolation is the groundwater flow, so this flowing groundwater right here is percolating. Okay, sometimes it will actually seep out up through the surface, and that's how you get things like springs. In some cases, the land dips below the water table, and we'll talk about that in just a second, and that's how you get a lake. But ultimately, it will also flow to the ocean. So one of the things that you should realize at this point is that everything will flow back to the ocean. Now, some of your precipitation is going to come in the form of ice and snow, and that can get collected into glaciers. It becomes part of the snowpack, and then once it's part of the snowpack, you actually can have sublimation occur, and sublimation is where the ice transforms directly into a gas, right? And so you get water vapor without that liquid phase. So that's sublimation. So that is the water cycle in a nutshell. All right, here is another little picture. Here are the descriptions of each of these words that you need to know. Oh, I forgot to talk about transpiration. My bad. Let's go back over here. So see this flora and fauna, right? We're interested in the flora. Plants transpire. So when they're doing photosynthesis and respiration and all this good stuff, as they are wont to do, they're releasing water in these processes. And that release of water is called transpiration. It's released onto the leaves. When it evaporates off of the surface of leaves, it is called evapotranspiration, and it is also a really important part of the water cycle. So that's how we're going to plug the biosphere into the hydrosphere. Okay, so here are all of those terms that I just asked you to know in terms of the action in the water cycle. Now, some other things that you want to know about are where is the water going to be held, right? Well, the big place that we want to talk about first are aquifers. Remember we talked about, so we've already talked about glaciers just a second ago. So the majority of fresh water is locked up in glaciers, right? Ice pack. But the next largest amount of water in the freshwater like category is going to be this groundwater. Groundwater is stored in aquifers. Aquifers are just the saturated portions of the ground, right? And so as that water infiltrates, it will seep down in between the pores of the dirt, right? And sometimes when you dig a hole, you'll actually dig a hole and you'll eventually get that hole filling with water, and that's because you've reached the water table. The water table is just the top of the aquifer. It's the line between the saturated zone and the unsaturated zone. So you can infiltrate, you'll hit this impermeable bedrock layer, and then the water will fill in those pores on top of it. When it's open like this and you can have water seep in anywhere, it's called an unconfined aquifer. Now, in some cases, remember that during the rock cycle, you should remember this probably from middle school, I would imagine, the rock layers, you get those impermeable sedimentary layers, right? But over time, as plates shift and things move, they can fold, they can tilt, they can fracture, and so sometimes you'll get one of those impermeable layers that goes up to the surface, and then there's a permeable layer underneath it, and then another impermeable layer, and so you get this band of permeable layer in between two impermeable layers. This is called a confined aquifer, and they will fill up with water too, but their recharge zone is very specific. It's just that area that's open to the surface where water can seep in. Confined aquifers lead to things like artesian wells. You can actually drill into a confined aquifer and pull water out. And we'll talk about unconfined aquifers as we start talking about things like hazardous waste. We'll talk about fracking. We'll talk about all those things. And confined aquifers will come up again and again in those conversations. Now, when we're talking about water resources, we're talking about groundwater, we're talking about water pollution. It's going to be our unconfined aquifers that we're going to talk about most. You can also sink wells into an unconfined aquifer and get water, and we do it all the time, actually. Now, here's the thing about that water table. When the land dips down below the water table, this is where you find your lakes. This is just groundwater that's above where the ground level is. Okay, I hope that makes sense. All right, so moving on. When we talk about that infiltration, I told you that all of the water will eventually flow to the ocean, but most of the time it's going to flow into an area where the ground is lower than the water table, right? And so if you have a relatively narrow, channel for that, you're talking about a river, right? Lakes are simply big, wide, slow parts of the river. So when we start talking about these streams and rivers, the infiltration zone for these is called the watershed, and this is actually the watershed for the Mississippi River. The Mississippi River is huge, and its watershed is also huge. So every single bit of precipitation that falls into this zone between the Rockies and the Appalachians is going to travel into one of the tributaries of the Mississippi, eventually into the Mississippi, and it will go to the ocean. So everything that falls in this area between these ridge lines, so the watersheds are bounded by ridge lines. The headwaters are where the source of the river is, so the sources are all in these mountain areas. The mouth is where it eventually flows into the ocean. Oftentimes there's an estuary or a marsh that is there, and everything that falls in this area is eventually going to get it into the big river and into the ocean. Okay, so there's a little bit about watersheds. This is going to be important to us. Interestingly enough, this is just a little tidbit. At one point, there was a proposition to actually do the state boundaries based on the watershed areas for each of the rivers, and if they did that, this is what the map would have looked like. It's kind of fun. Anyway, all right. So rivers and streams are really varied habitats because they start up in the mountains, right? And so they change radically from the source of the river all the way to the mouth of the river. And so at the source, you've got the cooler, clearer water. It's got high oxygen levels, typically characterized by freshwater fish like trout and bass. In the middle of the river, you've got, usually it's wider, it's warmer, it's more turbid, turbidity is the clarity of the water, and that turbidity is going to increase as the river slows and warms as you get towards the mouth, and it's picking up sediment. That turbidity decreases the amount of light, and so there's less photosynthesis, there's less oxygen in the water. The diversity, interestingly enough, increases at this point, and you're going to start to see fish that are capable of dealing with that lower oxygen level. Typically, you're going to be your catfish and your carp, and they will extend all the way into the mouth. By the mouth of the river, it's shallower, it's slow, it's warm, it's turbid, and there's way less oxygen. Okay, so that's kind of how rivers and streams change as they go through. And here are just some of the major rivers around the world, just in case you needed an example, you wanted to learn more about one of them. There you go. Now, what is the importance of water for people? Well, the obvious stuff: drinking, cooking, washing. Now, having said that, though, we also use large amounts for agriculture, for industry, for mining, for energy production, for waste disposal. And as the population goes up and as affluence increases, the use of fresh water is also increasing. So what do we do with it? About 70% of water on Earth, like our use of water, okay, let me rephrase that. About 70% of the water on Earth that we use, we are using it for agriculture. Another 25 or so percent, 20 to 25% is used for industry. And then domestic and municipal consumption is actually less than 10%. So when we talk about how much water you can save, it's great for you to do that, but and we should try and save water. That's a great thing. It's a noble goal. Having said that, though, it's agriculture and industry that use the vast majority of the water sources. Okay, so here's your first question. Although using water for irrigation copies the natural process of precipitation, it may interfere with the hydrologic cycle because the water disappears from the hydrologic cycle. The water consumed by irrigation is not always available for other parts of the water cycle. Water's destroyed in the process. Irrigation alters local plant communities and soil conditions, or both 2 and 4 are correct. Well, water can't disappear from the water cycle. Everywhere the water goes is part of the cycle. Water can't be destroyed because it just isn't. It takes a lot of effort to actually break up water molecules, and that doesn't happen in nature that way. So here's the thing. When you move that water for irrigation, you're taking it from where it used to be, and so you've moved it. You've changed the amount of water available in other parts of the water cycle, and you've changed the amount of water available for plant and animal communities, which also changes soil conditions. So both 2 and 4 are in fact correct. Okay, so when we talk about global usage, I already told you that 70% is used for agriculture, about 20% is industry, and about 10% is domestic. And agriculture use is going up and up and up. Now, interestingly enough, a lot of times you'll talk about how much water is used by a single person in the United States. And you'll end up with numbers that are like 120 gallons and blah, blah, blah. A lot of that is actually based on how much water we are using for industry and agriculture. And we do a lot of manufacturing in the United States, and we grow a lot of food. We grow so much food that we actually ship it all over the world. And so some of those numbers are a little bit skewed, but having said that, we definitely all around the world use lots and lots and lots of water for irrigation. Okay, lots of water for irrigation, right? Now, having said all of that, typical household water use, the big users are going to be the toilets and showers. The washing machine, just faucets in general, also take a large amount. Leaks, leaky faucets, leaky pipes, things like that, those are going to be big issues too. Okay, and then here I just put in here so you can see some of the amounts of water that go into making each of these products. I thought that would be fun for you. Okay, so water resource problems, they fall into 3 categories: too much water, too little water, and water contamination, poor quality. We want to start talking about too much water first. This is where we're talking about flooding, right? Now, there's natural flooding and there's human-induced flooding, and modern floods really can be much more destructive because we've changed the ecosystems so much that we don't have some of the buffers that we used to have, right? So when we think about pre-urban versus urban floods, and this goes to urbanization conversations, right? As we start paving stuff, we get more runoff and less groundwater, right? When we get more runoff, that means that we get more water physically on the surface. And that is what causes our big serious floods, a lot of our fast water issues, things like that. Okay. Now, the other thing that we do to increase flooding is we don't allow rivers to meander, right? We channelize them, which means that we build levees or we encase them in concrete. And when they do that, they don't have this big infiltration zone. So if your river overflows here and you've channelized it, then it's going to breach the levees and then it's going to flood the areas with all the houses. But if you have this natural floodplain available, as it overflows its banks, it's going to move into this infiltration zone, go into the ground, and you're not going to have problems with these housings. And so there's a big push to stop channelizing rivers and to rebuild some of those riparian zones. Riparian means the areas next to the river. To allow for flood control, okay? And so when we talk about the Midwest floods of 2008, for instance, and they've flooded again in 2013, and they'll flood again, right? These areas are so developed, or the rivers are so channelized, or they can be diverted and things like that, that we don't have the floodplains that we used to, and so that makes flooding a whole lot worse. And here's some example of the Midwest floods. Now, we also can see it when we build things below the water table. New Orleans flooded in Hurricane Katrina, not because of the hurricane. The hurricane actually made landfall in Mississippi, right? Wiped out Gulfport, Mississippi. But the catch is that New Orleans is in a bowl, so it's built below, and water is held back by the levees, right, from that hold in the Pontchartrain, right? Well, when those levees were breached, the water had only the city to go into, right? And so that caused massive flooding. So we do not help ourselves by limiting the places that water can go when we do have excesses of water. Now, let's switch topics a little bit and talk about water conservation, right? Because our next problem we want to mention is too little water. Here we're talking about drought and we're talking about aquifer depletion. Aquifer depletion is overdrawing of water, mostly for irrigation purposes, right, is why we're overdrawing so much. And it causes sinkholes, and I think we've seen sinkholes in the news, places like that, and then also subsidence. The land actually drops. And this is a real problem, right? Las Vegas, the area in Las Vegas, used to sit on a huge aquifer and had a whole artesian well system. Actually, it was a confined aquifer. And as the Las Vegans began to pull water out of that aquifer, it caused the land to sink as much as 3 feet in some places. So one of the downsides, besides just not having enough water when you have aquifer depletion, one of the downsides is saltwater intrusion. If you are living near the coast and you start, remember I told you all of that water is flowing to the ocean. Well, that gives you sort of a curtain of a transition zone between the freshwater and the saltwater because their densities are different and so they don't mix. But here's the thing, if you start sucking up all of the freshwater, then that salt water isn't pushed out as far and it starts to come up into your well. And this is what saltwater intrusion is, right? It's where you can't use the water in your well because you start pulling in salt water. This happens near the coast, right? It is definitely a coastal thing. But, you know, it's a huge problem. And then when we start looking at aquifer depletion around the country, so if you're in the interior of the country, your big problem is going to be less about saltwater intrusion and simply about the fact that you don't have any more water. In the coastal areas, like not here, but in the coastal areas here and over in Florida, as you start having this critical, moderate to critical depletion, this is where you're going to get your saltwater intrusion. Now, this is an interesting thing here because this area is a special aquifer. It's called the Ogallala Aquifer, and the Ogallala Aquifer is the largest groundwater deposit in the world. The United States sits on the largest groundwater deposit in the world. Having said that, though, we use it so fast, we've actually lowered the water table by more than 40 feet in some places, and eventually this water will be too expensive to pump out of the ground, and we will not have the water that we need for irrigation. The center of the United States, in between two mountain ranges, is a grassland. It's a temperate grassland, which means it doesn't have enough rain to really support irrigation, and the irrigation that we have, or to support crops. So the irrigation that we have there is coming out of that groundwater, which is not recharged as much as we are using it. So eventually what that means is if we can't get that under control, we could end up restricting the amount of food that we grow in our breadbasket because of our overuse now. All right, so what's your next question? It is, which of the following is not a means of preventing groundwater depletion? Reducing stream flow levels, banning new wells, taxing water pumped from wells near the surface water, or switching to less water-intensive crops? Well, you definitely do not want to reduce stream flow levels, right? That is a bad idea. You may want to increase infiltration zones, but you don't want to reduce stream flow. All right, so water shortages are caused by irrigation, all this good stuff, but they're also caused by water diversion. So when I was talking about channelizing of streams, one of the things that we do is we actually pull water away from river sources by building these channelized stream beds, which cause the flooding problems I was talking about earlier. But they take water away from it where it was before, and then we overuse it. And so when we start looking at stress on water systems around the world, water diversion is actually causing a huge amount of stress globally. Okay, and Mono Lake is one of the consequences that we've seen from water diversion. So Mono Lake, the rivers and streams that fed this lake have been diverted to Los Angeles because Los Angeles needs lots and lots of water. And so it's become way more saline than it ever was before, and you can see these are salt pillars, right? So not only has the water level decreased, this salt deposit is a big indicator of how salty it is, because fresh water has a certain amount of salt in it. That's how the oceans got salty to begin with, right? Is that as the water evaporated, the salt was left behind, and in the ocean, it's built up over the last like 3 billion years. This happens in freshwater too. It's called salinization, and we'll talk about it when we talk about irrigation more. Now, the court has actually ordered some of this water diversion to be reduced, but it won't be enough to restore Mono Lake, right? And the Colorado River is our really best example of this. The Colorado River goes through 7 states. It serves a population of somewhere between 25 million and 50 million people, but it's actually no longer a river because of the dams along the river. It's actually a series of lakes, so it doesn't flow. It's heavily diverted. There's a huge competition between urban and agricultural uses. There are water wars between Los Angeles, Phoenix, and Las Vegas. They are in court with each other all of the time. And here's the other thing. All of the water is actually used before it reaches the Gulf of California. 1993 was the last time that water flowed into the Gulf. This is the Colorado River in Mexico. Now, to compensate for this, the United States actually built Mexico a $2 billion desalination plant, and I'll talk about desalination in just a second. But we actually built them a desalination plant, which still does not run. Okay, because they've never turned it on. That's kind of sad. All right, so the other example of water diversion that we want to talk about is the Aral Sea. Okay, and the Aral Sea was the 4th largest lake in the world, right? And it began shrinking in the 60s when the Soviet Union diverted the water from its big 2 feeder rivers to irrigate cotton crops in Kazakhstan and Uzbekistan. Okay, and then during the 80s, they had essentially diverted all of the water, that there were years where no water reached the Aral Sea, and so the lake began to shrink, right? It evaporated, it shrank, and eventually it split into two different lakes, and there's kind of a little third lake here. And this was in 1997. It's much smaller now. And the inland sea actually is about 75% less than what it was before. So what are the results? So, because it's become more saline, like Mono Lake, the animal life and the plant life, done, right? And this is really sad because there was a huge fishing industry here and it employed thousands and thousands of people, and it is gone. There is a dead fishing fleet that just sits in the sand as a reminder of the greatness of this ecosystem. The other thing is, because of all the pollution that ended up in the lake because of the fishing industry, because of just industry in general, there are pollutants that are in the dust. So all of this dust, when the wind blows it, it actually blows up and it gets into people's respiratory systems, gets into people's lungs, right? And so cancer and respiratory diseases around the former sea have increased, as have infant mortality rates. And big lakes make their own weather. So the climate in this area has been affected. Summer and winter temperatures are more extreme because the water is not there to sort of balance them out. And so even the climate has changed. So this is a big deal, right? This is the biggest example, and you do need to know this. All right, so when we talk about global water problems, climate change, lack of drinking water, and population growth, and sharing water resources are going to be the big four things that we have to deal with. The thing about climate change is that it changes where water is distributed. The water cycle is still continuing, but the potential issues are that if you have reduced snowfall in an area that receives fresh water from glacial melt, and you're not replenishing the glaciers, then that glacial meltwater will not be consistent and eventually it will stop. The other thing is the sea level rise into aquifers, and then also, just if you start having sea levels rise in general, you'll increase that saltwater intrusion and you'll limit your drinking supplies. Many countries have insufficient water to meet drinking and household needs right now. So if you start shifting where that water is and you start contaminating it, and we continue diverting to compensate for those things, we're going to have huge drinking water issues. Population growth puts more pressure, right? Population growth puts more pressure. And so we have limited drinking water, and there are already many water scarce countries, which brings me to the sharing of water resources. Not all countries share well, right? And so it's not covered by international law, and international law is something you have to agree to anyway. And so you have geopolitical conflicts now, and we'll have those more in the future because of water. Right? And we've already seen it happen. The Rhine River is a really good example. Countries upstream in the Rhine River discharged pollutants, and then countries downstream had to pay for their water to be cleaned before they could drink it. And so they all had to get together and have this big have this big conversation about how to clean up the Rhine and all of this good stuff. And eventually they all worked it out together, but it was a huge cooperative issue. What if you have countries that are not super cooperative, right? The Nile is what we're seeing right now. So which two countries have conflict over the water in the Nile River? Ethiopia and Egypt, Sudan and Egypt, Egypt and Israel, Ethiopia and Sudan. Well, it turns out that Sudan and Egypt have had all sorts of treaties that they've had to work through in order to deal with the water in the Nile, right? And they are still having to work this out. They still have a huge conflict over it. So water conflict is a big deal. All right, so let's talk about how do we save water. Well, let's start with agriculture. So I'm just going to give you a couple of things that are great ways to save water in the three big areas, right? We've got agricultural. This is where we need to talk about irrigation a little bit. Irrigation right now is just essentially flooding your fields with lots of water or using center pivots, which are the big sprinklers. Okay, that ends up wasting a lot of water, and so the option is drip and trickle irrigation, which we will talk about when we talk about farming. Reducing industrial waste, one of the best ways to do that is simply recycle water within the plant. And lots of people are doing this, or they're trying to figure out ways to do this. It only works if the water is not used with like chemicals and washing. Sometimes you actually have to have a water treatment plant within the plant, and so there are some issues with it. But ultimately, it goes back to recycling is a great way to reuse your resource. The other thing is that you can provide incentives for companies to conserve water, and that you can do that with individuals as well. You can also do it on farms too. For municipal water waste, simply not using as much water is always like the go-to. Having said that, though, that's not always a possibility. So water efficient features like low flow faucets or low flush toilets, also using gray water. And this is the water that you wash your hands in. You can actually, this is not toilet water, this is like shower water, sink water. This can be used to flush toilets, and sometimes, depending on what your filtration system is like, it can be used to water lawns. You have to be careful about using it for landscaping though, because if it has a lot of soap in it, the phosphates themselves can cause problems out in the ecosystem. So mostly you look at gray water for flushing, but remember, the biggest draw in a house was water flushing. Okay, true or false, water meters reduce water waste? That is false. People actually will just pay, right? So what are things you can do to conserve water at home? We already talked about those. Here's just a list. All right, which of the following is a strategy to help use water more sustainably? More dams and levees, regulate water withdrawals, slow the rate of ozone depletion, or increase productivity in livestock production? Well, obviously it's about withdrawals, right? It's about withdrawals. So can we get new fresh water? The answer to that is no. There are, however, two ways to remove salt from ocean or brackish water. Brackish is not quite oceany. It's less salty than ocean, but more salty than fresh water. Still can't drink it. The two ways to do that are distillation and reverse osmosis. Sorry. Distillation and reverse osmosis. Both of these are very expensive and not super efficient. Okay, so you remember I told you about that desalination plant that we built in Mexico that they are still not running, partly because it's expensive, right? So distillation is the same thing that you learned about in chemistry. You boil the water, it evaporates, the salt is left behind, the water that's evaporating is condensing, and you can collect the pure water. Boom, done. If you want to do this on a really large scale, huge amounts of energy to do it. Okay, reverse osmosis is something that a lot of water treatment plants do already. Basically what you have is a salt impermeable membrane, and when we talk about water treatment, we'll talk about how reverse osmosis works just in treatment plants, but specifically for salt, and this is hard because salt is very tiny. NaCl, it's one sodium, one chlorine, or magnesium chloride or whatever, but it's very tiny. Okay, so you have a salt impermeable membrane, so this is on the microscopic level, or actually it's on the atomic level, and you shove the salt water through it. The salt stays in the impermeable membrane, and the water passes through it, and you have clean water on the other side. Yay! And that is it. This one went a little bit over 30 minutes, so sorry about that. But if you have any questions, please let me know in class, and I will see you next time.